Hi everyone. In 4.2, we're going to work on creating slope fields, which is basically your visual of differential equation. So I actually think it's pretty amazing. You can use the differential equation to help you figure out what slopes your solution curve would have. And then if you kind of just sketch those slopes in, you can picture what the different solutions curves will look like. So I'm going to work through an example. I think the big thing here is just to get you in to figure out how these slope fields are made. And then we'll answer some questions about them. But once you get that, I don't think that the questions are super tricky. But I think it's a really neat section. I love this section. So I'm going to work on this one, dy dx equals y over x. And what you want to remember is that dy dx means slope. So this is literally telling me that if I were to draw a solution curve, and we know that when we integrate, which is a way to solve differential equations, we get infinitely many solution curves. What we've seen so far is that they all differ by a plus c, but that can change. So here we're being told that of all those infinitely many solution curves, the thing that they share is the fact that their slope is their y coordinate divided by their x coordinate. So you can basically pick any point in the xy plane and you can think about, okay, do I have a slope and what would my slope look like? So to pick an easy one to start with, I'm just going to make a small grid here. I don't want to spend too long boring you with my working through, but just get you the idea. Okay, so this point, let's say this is 1, 1. The slope at 1, 1 would be your y value of 1 divided by your x value, oops, I can't talk and write, of 1, which is 1. So at this point, I'm going to try and draw a slope of 1. And it just needs to be a little, you're basically just drawing a tick mark to give you an idea of what that slope looks like. I can pick another point, 1, 2. And at 1, 2, my slope is going to be, I won't write down all of them, but it's going to be 2 divided by 1, which is 2. So these aren't going to be perfect, but you can kind of count these little boxes. So if we go over 1 up 2, it looks about like that. So my slope, and that's kind of wibble wobbly, but looks something like that. And then at 3, 1, my slope's going to be 3 divided by 1. So I notice that they're getting steeper as my y value gets bigger, which makes sense when I look back up at this fraction. If the top is bigger, the whole thing should get bigger. I'm going to work my way down now, and I notice something really nice when I go down to the point 1, 0. Since the top is my y value, the slope is going to be 0 divided by 1 is 0, and that's going to be true for every single point on the x-axis. Anywhere along here, doesn't matter what your x is. If the top of the fraction is 0, the whole thing is 0, so we're going to have these horizontal slopes. Ooh, I should be careful about this one. I remember to skip it, and then I went back and put it in. Well, we're thinking of zeros. That's a really good thing to kind of pick out what makes the whole thing 0. But also, when there's a fraction, we know that the denominator being 0 tells us something quite definite. We know that our slope is undefined whenever x is 0. So that can mean a couple of things. For a lot of what we see, what that means is that your slope is vertical, and that's why it's undefined. But we don't know for sure, so you can kind of, I don't know, mentally imagine this, but don't feel too stuck on it. It can also happen that there's a sharp corner there or something along those lines. So I'm going to actually leave these so I don't tie myself into that. But just remember that anywhere along the y-axis, your slope is undefined. Okay, to fill in a few more of these, so if I go down to 1, -1, I'm really tempted to say it wrong, then your slope is -1 over 1, so -1, and then this is going to be -2 over 1, so slope is -2, slope is -3. And you just kind of work your way along and see what happens. So for example, if I go to the point 2, 2, my slope is 1 again. And in fact, I can kind of spot a pattern there maybe, that anytime my y is equal to my x, the slope is going to be 1. So I can just work my way along the y equals x line and say, okay, for all of this, my slope is 1. You don't have to do that. You can just go point by point, but you can sometimes get some really neat things. You could also notice that if your y is the opposite of your x, then your slope is going to be negative x over x, -1. So for example, if I'm at -1, 1, then my slope is -1. And if I'm at -2, 2, my slope is -1. And I just don't want you to think this is always the case. The fact that the slope follows that line is not necessarily true. You could have something like, when my y is equal to my x, my slope is always 0, or when my y is equal to my x, my slope is always 3. There's lots of things, so that's kind of coincidence here. Okay, so I'm going to pause here, and that's about what I'm looking for you to do. Here, I can fill in a few more just to kind of give you the idea. It's steeper as I go up, and they're going to get steeper. Basically, the further away you get from the origin, the steeper these should get, so that's not perfect, but that's kind of what's happening. Your slopes are going to be negative if you're in quadrant 1 or quadrant 4. Sorry if that's making noise, my microphone's trying to fall. So this is the general idea, and I want you to work through a few examples. So the first one, your slope only depends on your x value, which can be really interesting. Your second one, your slope only depends on your y value, and then you'll do one like I just did where your slope depends on x and y. So I'm going to have you try those, and then we're going to look at all the answers to those together in your example 1 video, and we can then look at what the solution curve part of this is. So this is just to kind of get you going on what a slope field is, but I do want to work on what does it mean once you've got that picture going on. Okay, thanks for watching.